Good afternoon and welcome to Algorithms and Data Structures today. Last week we had this double lecture and worked on lists, and some of you joined the live stream, which was, I know, on a lecture-free day. Hope the others had time to watch the recording in YouTube. Last week when we discussed lists, we started with arrays and saw how they work, but we also saw their limitations, especially resizing or changing their size. So we work with dynamic arrays, which we also call lists, and they internally use an array, but we're able to create a new array, copy the entries, and encapsulate all of this behavior. We started to implement this, built the myArray class, looked at the complexity of the non-mutating behavior. And for the mutating behavior, we saw that actually appending could always lead to a resizing. But however, that resizing becomes more and more rare the larger our dynamic array gets, because we always double the size of the underlying array. And we analyzed this with amortization, and we introduced amortized complexities. And we would then say the appending is actually O of n, yet in average it's O of 1, but we still somehow need to, we cannot just write O of 1, we need to put some note there that this is an amortized complexity, because the worst case is still O of n. We looked at the concept of abstract data types and then introduced a couple of abstract data types, like a stack on which we always put something on top and remove it. We implemented a stack, looked at the complexities. We also looked at a queue where we append at the right end and remove from the left end. But we saw if we implement this with an underlying list and we do a pop at entry 0, always dequeuing, removing an element would be O of n. So we introduced a smarter concept, which is the circular array that we built. Then we also looked briefly at double-ended queues, and then instead of building array-based lists, what we did the whole time, we looked at linked lists, which is a totally different approach, and started implementing a linked stack and contrasted the differences of linked based sequences versus our array-based sequences. And for the majority of use cases, typically we use an array-based sequence because it needs constantly less space, typically runs constantly somewhat faster. Doesn't matter from the complexity framework, but still, if you use it in the real world, it does make a difference. And also these array-based sequences, they can get cached much better. So the theory is important, but there are also some real-world consequences. But that does not mean that the linked-based sequences are irrelevant. They're still relevant, and you need to be able to pick the right approach based on your use case. And there was plenty of coursework for lists, and today we had some students in the lab that have started with this. And I also talked about the coursework last week in a lecture. Now, we have introduced now lists, and we will look at more complex data structures like trees, maps, and hash tables. But especially to describe trees, we need, or to work with trees, we need a concept called recursion. And recursion turns out to be a very helpful concept also later for sorting, when we want to bring order into our lists, for example. So today and next week, we look at recursion. And concretely, we will look first today how we can actually search elements in a list, how we could maybe speed that up. We will see that recursion allows us to do something that we call divide and conquer. So we take a large problem and split it into smaller problems, solve the smaller problems, and then put the solutions together. And once we have built this, we may be wondering, actually, how can we determine the complexity of recursive functions? And for this, we need to explore so-called recurrence relations, and we will start then to solve them. And these recurrence relations help us to determine the running time complexity of our recursive algorithms. Solving these recurrence relations manually takes a little bit of time to learn. And for a certain class of recurrence relations, there's a so-called master theorem, which helps us to use a more structured approach, but only for some recurrence relations. And then we look at a concept called backtracking. And we also want to speed up recursion. And for this, we'll look at dynamic programming. So recursion is something very helpful, but you need to implement it correctly. If you don't do it correctly, it will lead to extremely slow programs. Um, Recursion is one way how we can describe repetition within a computer program. So far, what we have done is we have used loops for repetition, like a while loop or a for loop. And today, we will use recursion as an alternative concept to building programs that include repetition. Recursion is a totally different approach, and what we need to do is a function calls itself. Who of you has already worked with recursion a few times? Because this is a second semester course for most students. If you have explored recursion already, green sticker, and if you have not, maybe red one. That's a concept that for which I only get largely green stickers, but also some students disagreeing. This course will go far beyond the introduction to recursion that you had, because you most likely had that introduction when you had your programming one course or something like this. And we are starting now with a problem. We want to calculate the factorial function, like n factorial is 1 where n is 0. And for larger n, the n factorial is the product of n times n minus 1 times n minus 2 and so forth, 3, 2, 1. So 10 factorial would be 10 times 9 times 8 times 7 and so forth up to times 1. And we want to implement this function now with the toolkits we have available so far. And if we want to implement the factorial function, we can say factorial iterative for n. And we said that the result is 1. And this is just a simple implementation. So I don't catch any special cases like negative numbers, whatever, that could be put in for n. I assume I'm only putting in valid n's. If you take a software engineering course, they would cover also how to handle all of these exceptions, but this is not a software engineering course, rather it's an algorithm and data structures course. So here we just assume that only valid n's can be passed. And then I go through a range which starts at 1 and goes up to n, where n is included. So I need to put in a range n plus 1. And my result that I initially set to 1 will be multiplied by I, and we store this in res. So this would be just the implementation from before, because we're starting with 1, and then we're either done if the I is, for example, 0, and for larger ones goes from 1 up to n plus 1, so n is included, and we always multiply this I. We can just test the factorial iterative. If I pass a 0, it returns 1. For 1, a 1. For 2, a 2. For 3, it would return 6. For 4, it returns 24, and so forth. So this is the iterative way how we can implement the factorial with the tool set we had so far. And we had, in fact, so I have the code also here in my slides. We have just implemented this as a regular iterative function. But it turns out we can also express the factorial function as a function of itself, because we can say n factorial is 1 where n is 0, like before. And we can say for larger n's that the factorial function is n times the factorial function applied to n minus 1. And then this n minus 1 would be either 1 or it would return us n minus 1 times the factorial function applied to n minus 2. So it's a recursive approach that the function refers to itself. And it's actually a much more elegant description of the factorial function than this one here, because the factorial function now refers to itself. And we will try to implement this together. We can say we want the factorial recursive for n. And we first need the special case where n is 0, we return 1, because we've seen this in the definition before, where n is 0, I just return 1. And otherwise, I need to multiply n times the factorial recursive of n minus 1. But I also need to return this because I don't just want to calculate a local value, but rather return it. And now when we call the factorial recursive on, say, 0, it just returns 1. If I call it on 1, then it will return 1, where it puts here times the recursive call for 1 minus 1, which is 0. So it does a recursive call here that the function calls itself. And when that one is called, we see the edge case where n is then 0, because here 1 minus 1 would be 0 is passed. And then it returns 1, and then that function returns 1 times 1. And when you make this bigger, say for 4, you have more recursive calls, because this will always return another, or it will always do another recursion. And then once you have reached the edge case, then it will actually terminate. If you like using debuggers, it can be very helpful for you to test this at home and run this in an IDE with a debugger. And you can see that each time you call such a recursive function, it again puts something on top of the stack trace. So we introduced stacks last week, and I said stacks are needed in the operating system because each time you do a function call, you put something on the stack in the operating system. And this is something you could follow if you, for example, debug this. So we see that this function, it works different to the iterative one, yet it returns the same result. And now you're maybe wondering which one is better. This is something we will explore today. It's not really about better or worse, but it's two totally different approaches. And the student asked, would a loop be the best practice? We will later compare running times, and then we will see this kind of stuff when we look at a few more examples. But for this one, for the factorial, the loop would certainly be probably the better approach. Let's actually test it. Since one student asked, and it's in the private chat, it was sent to me, so the others did not see it. What we can do is we can call the timeIt function, and we've seen timeIt before in this course, and factor, we can call this for 10, and with timeIt, this is run many times, and we would see that the recursive one takes an average 296 nanoseconds, and we can also call the iterative one. I would assume the iterative one runs faster because we don't need to put anything on the stack and so forth. You see it's taking longer now, but it's running more experiments because the running time is less, and then it's being run more often. And we see that for 10, it's just run 10 times the amount of experiments, but we see it's 181 nanoseconds. And as we make this bigger, say we do now the factorial of 100, this takes 2.52 microseconds for the iterative one, and the recursive one We will see. Probably will be even a bigger difference. No, not too much yet. So 3.88 microseconds. But as you make your n bigger, you will notice a bigger difference. And there are also more complex recursions. This is a linear recursion, so we always have one recursive calls, but you can also have branching recursions. But let's test this again, that we have the iterative one on, say, 1000, and then we call the recursive one on 1000. So the iterative one is 193 microseconds. The recursive one, yeah, not too different yet, but maybe there's also some optimization going in the background through the interpreter. But overall, you will later see more complex recursions like branching recursions, which will make even a bigger difference. But we see for this example, yeah, the iterative one is the one we should pick because it definitely runs faster. And also, it's easier to debug. There's a question if there are established functions. Well, they come with libraries, and you can check the math library, what's in there. But we've just tested, or we've just wanted to implement this as one initial simple example for us. When you want to use the factorial in your code in a bigger software, obviously don't implement it from scratch. Rather use a library to do this for you. And we will later also see how we can maybe speed up some recursions. So this was just an initial example. What we see here is the recursion trace. Say there is a call of factorial, so the recursive one for value 5. Then it calls it for 4, then for 3, then for 2, then for 1, and then for 0. And for 0, we have the edge case where we return 1. Then we go back in the stack to factorial 1, for which we got the 1 back, and it returns 1, which is this one here of the parameter, times 1, the one we got returned, which is 1 to factorial 2. And this returns 2, which is our parameter value, times what we got out of the previous recursive call, returns the product 2 to factorial 3, and this one returns 3 times 2 what was returned, and so forth. So this is how you need to call, or this is something we call the recursion trace, or sometimes recursion tree. And you may be asked at some point in an assignment maybe to draw the recursion tree or recursion trace for a specific function. It would be something like this, in which you would visualize the recursions until it terminates and returns the values. Now, what I want to implement with you is a sequential search. So a linear search is or also called sequential search, works the following. We have an array which has these values here: 2, 4, 5, 7, 8, 9, 12, 14, 17, up to 37. We have 16 entries, which index is 0 to 15, but could be an array or a list, whatever. And we want to find if a specific value is in that list or not. You have definitely seen something like this maybe in a coursework or so. So it should be fairly easy to implement this. We will test it. We will try it together. So we will do the linear search. What we pass is the data, which is just a list for now, and the target, the value that we are looking for. And what we need to do in a linear search is the example data we saw was sorted, but we don't require the data to be sorted. It can be unsorted. And we go through the entries. So for value in data, it's a for each loop, and we check if value is equal to the target, I return true. If I find the value while I go through to the loop, I return true. The target was found in the values. If the loop finishes, that means we have not found our value. We're returning false. And we can test this now. We can say our data is, we do integers for now, 2, 1, 9, 25, 120. Well, we avoid duplicates for now, 30. And we want to do a linear search. We say on the data, I want to find out if there's a 1 and it returns true. I want to know, is there a 20 in it? It returns true. Is there a 50 in it? No. What do you think is the complexity of this linear search? If you have any suggestions, send it to the chat or turn on your mic as you wish and discuss with us what you think the O complexity, worst case, is of the linear search. We got an answer in the chat. Do you want to tell us, maybe turn on your mic, why you think it's O of n, so we can discuss it together? It's also a bit of a revision of the complexity we've done before.
In the worst case scenario, the search element will be in the end of the list. So we should go through all the elements in order to find if it's there or not.
Correct.
Or won't be in the list, and again, we should check each element.
Yes. So in the worst case, the last element is the one we are looking for, or it's not in at all. So I need to look through all elements. Obviously, the best case is O of 1 because the first entry could be it, but this is only secondary. We always care about the worst case. So worst case is O of n. And now we are wondering, can we do better than O of n in the worst case? Has any of you ever seen an algorithm that allows us to search faster than O of n? Without maybe looking at the slides. If you think we can search faster than O of n, maybe send a green sticker. If you think this is not possible, send a red sticker. Well, some positive reactions. It turns out we can do faster than O of n if we assume that the data is sorted. So that if the data is unsorted, it's O of n. But if the data is sorted, so we don't know yet how to sort the data, but it's something we will see very, very soon. Or not very soon, but in a few weeks, we'll explore sorting. But for now, we just assume we can sort data. And we can sort integers in an increasing way, in an ascending way. So the smallest integer would be leftmost and the largest integer rightmost. And then we can do something that is called binary search. And binary search does a search on unsorted input and tells us if the element is in there or not. And what it does is the following. So I have two helper variables, which are called low and high. And low is the lowest index, initially 0, and then the high index is 15, the maximum index. So we're initially looking at the whole data set. Then we are looking at the middle index. So what is between low and high? And that would be here index 7. And this is element 14. And now we're looking for some value. Say we're looking for value 14, then the middle value would be just the one we're looking for, we can return true. But now imagine we're actually looking for, say, value 22. What we see, because this is sorted, we can then see what's the value of the middle element, which is 14. But we are wondering, is there a 22 in or not? Then the consequence is we don't need to look at the left half anymore, but only at the right half, because the right half is now interesting, because the 22, the value we're looking for, is greater than the middle one. And the middle one is not the value we're looking for. So I can update the low index And I can say the low index is the mid index plus 1, because the mid index I don't need anymore. I've already looked there. So the low index becomes mid plus 1. Now I have my low index 18, and 15 is the maximum index. So the middle index is 11. And we have in the middle value 25. 25 is not the value we are looking for, but 22 that we are looking for is smaller than 25. So what I'm doing is I say, well, from this right half that I had here, actually only another half matters, because 22 is not greater than 25. So these elements here don't matter. So only the elements between indexes 8 and 11 matter. Then we update the high index, which is the middle index minus 1, because the middle index already was explored. We don't need to look at it anymore. And then low is 17 as before, high is 22, which are indexes 8 and 10. So the middle index is 9. And middle index 9 is value 19, which is not the one we are looking for. So I know that if I'm looking for 22, it must be to the right of 19, but only in this interval that still matters. So I'm updating the low index, and the low index is then the middle one plus 1. So 9 plus 1 is 10. And in this case, the low and high index are the same, both 10. So the middle index is 10. And then I'm checking if the value that I'm looking for is 20, or if the value I'm looking at is the one I'm looking for. And if that's the case, I'm returning a true. If it's not the case, here I would be returning a false, because I have looked at the minimum interval possible. Say if this was not a 22, but a 21, there wouldn't be any other values to be able to look at. And then I would return false. And this is binary search because in each iteration, it actually halves the space that I'm looking at, but it assumes my data set is sorted. Has any of you studied such an algorithm before? Maybe thumbs up or thumbs down if anyone has come across this. I came across this stuff when I was maybe 14 years old or something, and I looked at some algorithm books on my own. So some students have. Perfect. So what I need is I need to sort my data. And what you can do in Python is you can call sorted on a list, and it will return it sorted, and it returns a list, and I want to store it in data. So data is now sorted. That's what we require. And from here, we can just try to implement the algorithm from before. We can say search binary, and I want to look at the data and figure out if there is a target in it. I also need two helper parameters, which are high and low, or low and high. In Python, I can assign a default value to them. So I can say low is none and high is none. So if I call search binary, I need to pass a value for data and target. I can assign values to low or high or not. And if that's not the case, they are none. And why do we need them? We will see this later because we will implement our binary search in a recursive way. But we will say low, if low is none, we will assign 0 to low, because this would be just the initial call. When you call binary search with your data and your target, you don't want to worry about what these indexes are. You just want to search. So you don't pass anything for low and high. And that means low is none. So we will put it to the minimum index possible. And if high is none, then we will say high is the maximum value. The maximum value is the length of data minus 1, because the length, so we have 10 elements, so we want index 9, the maximum index, to be high. Later, if we don't find our element, we've seen before, we found our element when our interval only had one element left, which was the worst case actually. We said this is a 22, which we looked for. But if it was 21, we would somehow need to escape and return from there, or abort and return from there with a false. And this false will actually be returned if it ever happens that the low parameter or the low variable is greater than high, and then we don't have an interval to explore anymore. We will later see how this can be created. Um, However, we have also, I'm just separating this a little bit, that it's just separating these ifs. So we have these two ifs up here for these special cases, and here we're checking when to abort. And now we just want to implement the procedure from before. I said we need the middle index, and the middle index between low and high is something we get by adding low and high and divide this by 2. And it's an integer division, because in Python by default we have a float division in Python 3, which is different to Java. But we want to have an integer division, so we divide by 2, which is an integer division. And like this, we also round down in case this value here is odd. But that doesn't matter. And then we always checked when we have our when we have our middle index, we wanted to check if in the middle is our target. Because middle is the middle index between low and high. We go to this index, which returns us a value. And if that value is our target, that's exactly what we wanted. That in the middle, we have the target and we are done. But there are two other cases, and we've discussed them in the example. It can happen that the target is less than the value in the middle. And if that's the case, I only want to look at the left half. That's what we visualized before. So I need to return, and I'm doing this in a recursive way. Yeah, sorry about this. I don't want this. Don't know if I'm getting bothered with some pop-up windows. I don't know if you see them. No, they're gone. Still not gone. No. Um, we're doing a recursive call on the data or with data, and we're looking for the target, but now we update the low and high indexes. The low index stays as it is because we said the target is less than the middle value. So the low index stays, but we're only looking at the left half of the interval. And that's why we say the high index will be mid minus 1, because we don't need to put mid there, but mid minus 1, because we've already looked at the middle one. And we are doing a recursive call, and whatever this returns, because this recursive function may do more recursive calls, and at some point it will return true or false, and this is what we want to return to the caller of this call. And we have a third case, which is just the other half. So we have three cases. Either the target is the middle value, or this is one case. The next case is the target is less than the middle value. And the third case would be the target is greater than the middle value. So we just put an else here. This is the last possible case. So we say we're doing a recursive call with data and target. The high index stays because what we want to look at is now the right half of the interval. So high index stays, but the low value becomes mid plus 1. So we have implemented the binary search, just what we had visualized before. We can test it now. We want to do a binary search on our data, and we want to see if value 100 is in. And it returns true because this was our data set from before. Value 1 is in, value, say 23, is not in because that's not part of our data set. So the binary search is fairly easy to implement. And with such a recursive way, we can describe this quite well. We can say, well, we're doing a recursive call with data and target unchanged, but we change either the low or the high index. You can think as a homework how you can convert this binary search into an iterative one. This can also be done by a loop without any recursion. It isn't that difficult, in fact. What you would have is don't have these two parameters anymore. They would be local variables, which would be just 0 and high would be length of data minus 1. And then you would just put a loop here, and rather than doing the recursive calls, you would amend the adequate indexes, and you would also move the false statement into the right place, or where you return the false. So this can be converted to a loop very easy. Something you don't find in the coursework, but something I had put in the exam a few times. And maybe this will help you to get some practice to convert a recursive function into an iterative one, vice versa. Do you have any guess what, without looking at the slides, with what the computational complexity, so the running time complexity of binary search could be? If you have any guess, send it to the chat or turn on your mic. I want to see if there are any suggestion what the complexity of binary search could be. I'm also putting the visualization here. One student says O of log n. Do you also want to tell us why you think it's O of log n? You can turn on your mic and tell us, or in the chat. If you tell in the mic, it's good because then we get to talk to you. Well, let's see if you'll send. One student says because after every iteration, the search is halved. That's correct. We search the interval we are searching gets halved, but still we somehow need to argue how this can lead to a logarithm complexity. So O of log n is correct. We will later see some tools how we can actually determine this. So we are not doing this right now, but we'll do it later. But for now, just bear with me that the complexity is O of log n. And it's enormous because it's an enormous speed up. It's actually an exponential speed up because, say, you have 1 billion entries, then the log 2 and rounded up is only 30. So rather than maybe a billion comparisons in here, you only need to take about 30 iterations in the worst case. So this leads to a massive speed up rather than the worst case, a billion checks. With this one, it goes much faster. But we'll analyze it later. We will now look at some more recursive algorithms, and we will see a design pattern that is called divide and conquer. Divide and conquer is one of many algorithm design patterns, and this helps us to describe algorithms and solve certain computational problems in a very elegant way. What we want to do is we have a very complex problem that we just don't know how to solve as is. But maybe we can divide this input into smaller problems, make them smaller and smaller until they are so small that we can easily solve these subproblems. This is the conquer. So we divide a big problem into smaller problems until they are so small that we can easily solve these small problems. And then we put all the solutions together again. This is the combine phase. So maybe there's a huge problem, we don't know how to solve it, but we know smaller instances that we can solve. And if we can break this big problem into smaller problems, solve them, or find people to solve it, and then put it all together, this is quite helpful. This is actually what binary search does. Because with binary search, we're looking at this big, we're looking initially at this big list, and we don't know how to determine whether there's actually the element in or not. But we make it increasingly smaller because we always halve the interval until we're done. And the concept of divide and conquer is something we'll see in a few weeks when we look about 2 lectures from now, when we look into sorting. And when we have a big data set, we also don't know how to sort it, but maybe we can break it into small data sets, small single elements that we can sort, and then increasingly put that together again. And there's, for example, quick sort and merge sort that take advantage of that concept as well. And there's a very famous example about divide and conquer from the literature. It's the Towers of Hanoi. What is it? So in the Towers of Hanoi, you have 3 of these sticks. And on each stick, you can put such disks. And it turns out that all disks have a different size. There are small disks up to big disks. And on such a stick, you can put n disks. But there is a requirement that you're only allowed to put smaller disks on top of bigger disks. So that's the sorting. You're never allowed to put a bigger disk on top of a smaller one. Only smaller ones on top of the bigger ones. It doesn't matter if it's a very big one and a very small one, or very big and almost very big. But the sorting, the order is simply only put smaller disks on top of existing disks. And now your task is you have all these disks here as this stack, and it's your task. So this is stick A, and you need to move it to stick C, and you want to move this stack to over here, but you're allowed to use this stick in between, stick B, but you're only allowed to move one disk at a time. And your goal is to have this tower exactly as is over there once you're done, but you're allowed to use all the sticks as you wish, as long as you always move one disk at a time and you never put bigger disks on top of smaller disks. So you cannot just put a small disk here and then the next bigger disk on top and so forth. That would be a violation. So you somehow need to work with these disks. It's very simple if you have one disk. Say you only have one disk here, you can just move the disk over here. If you have 2 disks, you could move the small disk to the helper stick, then the big disk to the final stick, and then the small disk from the helper stick to the goal stick on top. So for 2 disks, it's easy. But once you have more disks, it actually becomes more complex. Again, without looking at the slides, what do you think, how many lines of code we will need to implement the Towers of Hanoi? We want an algorithm that can solve it for us. I'd like to see some guesses in the chat. What do you think, how many lines of code we will need now to build an algorithm that does the Towers of Hanoi for us? I'd like to see some guesses. And the algorithm should be generic, not just for 1 or 2 disks, but for an arbitrary n disks. I'd like to see some guesses from you in the chat. So 5, 10, 20, 12. It turns out it would be less than 10. So we can do this actually quite easy. I know when you see this for the first time, you think it's complex, 20 lines or maybe even more lines. But we'll test this now. So we call this Towers of Hanoi. We want to run this for n disks, and we have 3 sticks. We have a source stick, the one from which we take, and we want to move our tower from A, the source one, to the target one, which is C, and we have a helper stick, the auxiliary one, and this is B. So just a setting from before. We want to move a tower of height n from the source A to C, and we can use a helper if we wish. Now, with divide and conquer means we have this very big stack of disks, and somehow we need to move it now. But maybe we can break this down to a smaller problem. First of all, there's always some edge condition. It's extremely easy if there's only one disk. So if there's one disk, we say we move one disk, disk number one, from somewhere to somewhere. And these are just the parameters of our string. And we want to move from the source to target that one disk, and we're done. And we can just return. So return doesn't return true or false. We just return, we're done in Python. So this is fairly easy. So we say move disk one from, this is a parameter, to here, and the first parameter for the 0 is a source and target. So from A to C, and we're done. But now it becomes more complex for larger n's. We need a recursive call, and we can say, typing it first, we can try to make this problem smaller. So we have a stack of n many disks. What I can try is I can have all the disks except the biggest disk. So all the n minus ones from the top. So all except the biggest one at the bottom. I can move them from the source, so from A to B, the auxiliary one, and I can use the target as the auxiliary one. Because remember, the first one, or this parameter, is for the source. Source just stays, I move it from to the target, which is the auxiliary one, and I can use the target stick as a helper. Once I have moved my stack of n minus 1 height, I can actually just move the biggest disk from, so n is the parameter, so the nth disk, the lowest one, I can move that one from the source to the target. Because what I'm doing is I move all the top ones, n minus 1's top, from the source to the auxiliary, somehow using the target as a helper. But when I'm done with this recursive call, all the top n minus 1's have been moved from the source to the auxiliary. Target is free. Then I'm moving the last one from the source to the target. And then I move this remaining stack that I have also over. So I move the n minus 1 remaining ones from the auxiliary, where I have stored them, to the target, and the source can be used as the auxiliary one. And this recursion may obviously go quite deep if n is big. We can test it now. We can say the towers of Hanoi, we just have one. It's fairly easy. We move one disk from A to B. We can move two disks. And there was a typo. The slides is obviously without the typos. So it's towers of Hanoi. We'll test it again. So we moved that one disk from A to C, which worked. Now with two, we move the top disk from A to B, then the bottom disk from A to C to the goal. So B is the auxiliary. And then at one disk we had put in the auxiliary, we move to the goal to C and put it on top. And obviously, you can put in now, say, 5, and we get the procedure what we need to do. You can test this at home with a stack of, I don't know, some items or books, whatever, that are of different size. And you can maybe try it for 4 or for 3 at home. Try it for 4 and see if you get an optimal number that you can come up with. And all you need to do is remember, these are recursive calls, which may lead to more recursive calls. Because obviously, if n minus 1 is still big, you cannot move the whole stack over. But with the recursion, you break this again down to n minus 1 minus 1, n minus 2, and so forth until you are in the special case. You can do this for 5, you can do this for 8, and you see for 8, it's quite a lot. Maybe don't try this for 8 at home because your weekend will be over, but feel free to test this. And we saw it's just a few lines of code. So 1, 2, 3, 4, 5, 6, 7. 2, 4, 6, 7. So there's a very good question. So with every additional disk, the number of moves doubles plus 1 is the question. It's a very good observation, this doubling behavior, and I agree with you. So this actually has exponential growth. Where we can put in 10 and we see it gets ever longer. Very good observation. You see here, actually, we start to move the bottom disk over from A to C. So this is just half. And there's a question if the complexity is O of 2 to the power of n. And that's correct. And probably the others are wondering why. And that's a very good question. So again, the algorithm runs in O of 2 to the power of n. That's a correct observation. The beauty of the towers of Hanoi is, I mean, it's a toy example, but it shows us that with just divide and conquer, with a few lines of code, we can solve this problem very elegantly. Now, why is it O of 2 to the n? Similar to before, the binary search, we will do a formal analysis very soon. I'll show you very soon how to do this formal analysis. First, there's a little bit more content, and then we'll do the formal analysis. Recursion has an advantage, often leads to very clean, very short code. And for certain computational problems, it's quite intuitive and natural to think about the solution recursively. Not for all problems, but for some. Recursion will be very helpful when we look at trees in a couple of weeks. In about a month from now, we will start working on trees. And for this, recursion is very helpful because a tree starts with a root node which has more children, and each of these nodes has more children. So it's actually a recursive data structure. Now, there are some challenges. Recursion uses more memory, more running time. Recursion can also be quite slow. In particular, if we have a binary recursion, so a recursion that is not just linear but branches out, which is also a multiple recursion. We see some examples very soon, but you can implement them better, and then maybe the recursion is not that slow. So there are some tricks, but it leads to more memory because each recursive call adds some space on the stack in your operating system. And if you have too many recursive calls or too many function calls on top of each other, this can lead to a stack overflow. So now you know the website Stack Overflow, why it's called Stack Overflow, because you're running out of stack in the operating system. And recursion is also often harder to debug. That's a reality because all the stack trays. So an iterative function is often much easier to debug. We will test something now. So what I have in the slides, I will just implement now with you. We will implement the Fibonacci numbers. So the Fibonacci number is something you have probably seen before. The Fibonacci number of 0 is 0. The Fibonacci number of 1 is 1. And in general, the Fibonacci number of n is the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2. So the Fibonacci number of n is the sum of the two previous Fibonacci numbers. And we have these edge cases for n 0, it's 0, and for n equals 1, it's 1. What we see here is it's a binary recursion because we have a recursion here and there. So we're not just returning a linear recursion like we did before, but rather it's binary and it's branching out. And this stuff, if not implemented correctly, tends to become extremely slow. We can call the Fibonacci number of 10, which is 55. The Fibonacci number of 3 is 2, and then of 2 it's 1, and then of 4 it's 3, of 5 it's 5, of 6 it's 8. So always the sum of the two previous ones. But it turns out this becomes quite slow if I put in, say, value 30. And this time I'm just doing a one time, not a time it. We just do one measurement. So the Fibonacci number of 30 is 100 milliseconds already. Of 35, it's 900 milliseconds. So let's test 38. So the Fibonacci number of 38, it's already taking 4 seconds. And of 39, it keeps ever growing very, very quickly, as you see, even though the function is just like this and n is still surprisingly small, but it tends to become quite slow. Why is that the case? Because when you have this Fibonacci number of n minus of n, say n is 10, then this leads to a recursive call of the Fibonacci function for 9, which is n minus 1, and 8. But the 9 leads again to a call of 8 and 7. And that 8 leads to 7 of 6, the 7 of 6 and 5. So, and the same here. So what you get here is a recursion tree that keeps growing super, super quickly. And what you see is, for example, when we say the Fibonacci number of 10, this is the Fibonacci number of 9 and 8, but the Fibonacci number of 9 is the Fibonacci number of 8 and 7. So down here, we compute it for 8, but over here also. So we do a lot of duplicate work with this branching recursion when we try to implement it. And even for a number like 39, it tends to become already quite slow. So because we do a lot of duplicate work, and feel free to draw some, at least the beginning of this recursion tree. And you see there are a lot of duplicates. And these duplicates, they always get recomputed. We don't have a cache where we are storing this. So this is a super inefficient way how to calculate the Fibonacci numbers. But it turns out there's help. What we can do is, so we saw the Fibonacci number of 39 is 6 seconds. We can try to implement this now in a different way. What we need is a so-called LRU cache. Caches are essential in computer science and in computers because we don't want to compute values over and over again. And an LRU cache is called the least recently used cache. So in an LRU cache, say I have 100 entries I can store in there. And when I want to compute something, I first look into the cache if it's stored in the cache. And if so, I don't compute it. I take it from the cache. And if it's not in the cache, I will compute it and then I will store it in the cache. But the cache can say only take 100 entries. So I'm deleting the entry that was least recently used. So I always want to keep the most recently used values. And I can maybe, so the cache is a temporary storage and it has nothing to do only with recursion. You have a cache also in your CPU, in the operating system, in various pieces of your computer. And a cache, you can make a cache bigger, but then it needs more memory. Maybe increases performance, but needs more memory. So you need to make a trade-off again between computing time and memory. And it turns out we can use in Python the LRU cache from the function tools. And this is something we can apply to our Fibonacci function. So we're importing this. And what we need to do is LRU cache is now a so-called decorator. I'll explain you in a moment what a decorator is. Say we say fib1, and we just implement fib1 as before, and then I'll tell you what the decorator does. So we said where n is 0, we return 0. Where n is 1, we return 1. And otherwise, we return, and here it's now fib1, it's our new Fibonacci one, of n minus 1 plus fib1 of n minus 2. Now, what does this mean? This is a so-called decorator. And a decorator allows us in Python, and this concept exists in other languages too, not in all, but in some. When we use the LRU cache decorator. So this allows us to add a cache to our function. It's already implemented in Python natively in a library. Next week, when we continue with recursion, we will see how to implement such a cache on our own, but that's not relevant for now. But this cache works, as you need to imagine, when we call our function with an n, the cache internally first checks, was this already computed for n? If so, I'm returning it and I'm not computing it. If it was not computed, I will compute it. And once it's done, I put it in a cache. And if the cache gets too big, we can also customize this cache. We kick out the least recently one used. Now, we've seen it takes 6 seconds to run this on fib. I want to see some guesses from you. What do you, without please looking at the slides, because they're all in the slide. What do you think how long it takes if I use this cache on fib1 and I put the value 39 in? Rather than 6 seconds, how long do you think it takes? One student says 2 nanoseconds. It will probably take a little bit longer than 2 nanoseconds, but it will be substantially faster. Concretely, it takes 31 microseconds. So a bit more than 2 nanoseconds is too fast for the work that needs to be done. But maybe with a future computer. But we're at 31 microseconds. Because what it does is, it calls this on 39. Obviously, for 39, it's not in the cache. So it goes in, calculates this for 38 and 37, but for 38, it also does not exist. So it does it for 37, 36. And once it stores in the cache, say once, so we have some recursive calls here, but once it reaches the n equals 0 and n equals 1, these are stored in the cache. Then, if we compute it for 2, it's computed once for 2, which takes the cache values for 0 and 1. When we compute 3, when we compute it the first time, we take from the cache for n equals 2 and n equals 1, add it and store it in the cache. So we have this huge branching recursion, but it will not expand that much anymore because once we have stored it for n equals 0, n equals 1 in the cache, then for 2, wherever we call it for 2, we just take it from the cache and we don't expand it. And so when this one here computes it for 39 and 38, sorry, for 39, so this is 38 and 37. For the 38, we compute it for 37 and 36, but we don't need to always recompute it because once we have stored it for an n in the cache, which keeps growing, we just read it from there. That's why in order to have a fair comparison, I also use the time and not the time it, because with time it would, um, this would unfairly benefit from the cache when you run the same. But what you will see is if, and this is still stored in the cache, so it's in my live session, the program has not terminated yet, so I still have the cache, and if I call this now for 45, it still uses what is stored in the cache up to 39. And we see this takes only 11.9 microseconds. And I can call it for 100 and it goes super fast because whenever we build a bigger one, we store it in the cache. And if you try calling this on 100, good luck. This will probably not finish for the rest of your lifetime. But this one here just takes a couple of microseconds. But you're storing this in the cache. Next week, I mean, we still have lecture for today, but next week I will show you how you can build such a cache on your own. And I told you before that recursion can become very slow, especially branching recursion, if not implemented correctly. Ideally, when you use recursion to implement an algorithm because you have a concept that you can describe well in a recursive way, if you can get rid of the recursion by rewriting the algorithm a bit, that would be very helpful. Some kind of recursions are very easy to remove and some are more difficult. One that is very easy to remove is a tail recursion. What is a tail recursion? For example, this one here, where we have a return, which is just a single recursion. This would be a tail recursion. Or we could also think about when we implemented, we could also implement a linear search and think maybe there is a tail recursion. But try this out at home. A tail recursion would be a single return of a recursive call. These tail recursions can oftentimes be removed quite easy. Big note, this one here is not a tail recursion because I'm not just returning the result of a recursive call, but I am multiplying it with n. So this is not a tail recursion, the n times factorial recursive, while, for example, for the binary search, we have a proper tail recursion. These tail recursions can typically be removed very easily. Other recursions are more difficult to remove. Now you're wondering, are loops as powerful as recursions? Yes, both are equally powerful. So you can always convert loops into recursions and recursions into loops. It's easier to convert loops into recursions usually. Converting recursions into loops is oftentimes more difficult. What you often would need to do if you really try to do this, that you get rid of a complex recursion and turn it into some loop scheme, what you would need to do is you would often need to manually handle a stack. So you would need to manually, or you would need to emulate what you're putting on the stack. Not for the tail recursions, but for more complex ones. For example, for the Fibonacci numbers. So now you've seen the pros and cons of both recursions as well as iterative approaches. And both are equally powerful, but obviously doing such a conversion, a very complex recursion into some iterative code is not that straightforward. And there are ways to tune recursion, like we've seen with the LRU cache. This doesn't work for all recursive problems, but for some. And next week, we will see how we can build such a cache on our own, or we will see dynamic programming, which allows us to work on recursions efficiently. But today, we are still interested in determining the running time complexity of recursive functions. Because we have seen before the binary search, we have seen the towers of Hanoi, and I promised you that we would look at today how we can determine the complexity of such functions. This is so that's why it's helpful if you're up to date with the coursework and the lectures where we looked into complexity theory. And we will now work with so-called recurrence relations. And a recurrence relation is an equation that expresses each element of a sequence as a function of the preceding ones. You probably are wondering, what does this mean? But what we need to do now is we need to describe our recursive algorithms as or their behavior as a recurrence relation. And then we can try to solve these recurrence relations. I will show you this now. We've looked before into binary search. And for binary search, we will describe its behavior now as a recurrence relation. What we knew is if binary search only looks at a single element, we are done. And what this means here, this recurrence relation, is if we look at one element, we only have a constant amount of time. So T of 1 is 1. And we only look at one element, and that's either the element we're looking for or not. If I look at n many elements, then in the worst case, I need to look next into half of the elements. Obviously, if I'm looking at n elements and the middle one is the one I'm looking for, I'm done. But we're interested in the worst case. So in the worst case, where I have n elements, I need to look in the next step at half that many elements because I'm looking at the left or right interval. Plus, I have some constant work like for these checks and updating the indexes. So this is some constant work, a few operations, but if it's 1 or 5 operations, doesn't matter. And what I need is always, I need to see how T of n depends on itself. And I always need a corner case when I'm actually terminating, when I'm done. And now what I need to do is I need a solution. So I need to find a solution of this recurrence relation. So I'm also writing here, this is a recurrence relation. What I'm deriving now for you is also available in the slides, but we developed this together now. And when I solve this, I need to find out if there is some pattern. So I know that T of n is T of n half plus 1. And what I want to do now is, so I had done one step. I've looked at all the n elements, and now I look at half of the elements in the next recursive call. And I assume the worst case. I always assume I need to split further. I haven't found the element in the middle. So in the worst case, I need to half of the interval. So I need to say this is then T of 4, T of n divided by 4, because I halve the half, plus I have more constant work. Plus I have this old constant from before. So this is this one. And what I had here in blue, I've done here now. Now I'm still not done. Now I need to look at another recursion. And 4 divided by 2, n divided by 4, halving this again, is T of n divided by 8. Plus, I have another constant work. Plus, I have these old constants before. So I'm putting them in colors here. this is the one from here, and so forth. Do you see some pattern of what this is leading to? If you see some pattern in here, tell me. And you can send this to the chat or turn on your microphone if you see a pattern in what I'm doing in here. If you see a pattern, maybe send me a thumbs up or something, so I'll wait for you. If I don't get a reaction, I assume no one here sees the pattern. So we see some positive reactions. Do you want to tell us what pattern you see? Maybe turn on your mic, this would be easier. Well, I'm not getting any answer, so I'll see. Now we got this. One student says it follows the pattern n is divided by 2 to the power of k, because we had divided by 2, 4, 8, 16, so 2 to the power of k, plus we have k many constants, because all of this here are these constants, and they lead to this k. We have so for each iteration, we have one more constant. So I have k many constants. Now, we keep doing this until we achieve, until we make the interval as small as possible. So n divided by 2 to the power of k. When does all of this stop? When we only have one element left. So I need to keep doing this procedure until I only have one element left. So we need to say n divided by 2 to the power of k must be 1. So we know, and we need to solve for k now. We need to know, how does k depend on n? Because n is the input size. So we can say n is 2 to the power of k. So I just multiply this with 2 to the power of k on both sides. And I also know, if I solve for k, that k is the binary logarithm of n, because I apply the logarithm here, which is log n, and this is the log of 2 to the k. So I can move the k forward. Well, I'll just put this as a note. So log n is the log of 2 to the k, which would then be equivalent of log n is k times log 2. And then I divide by log 2. So log n divided by log 2 is k. So this is just in green, some note. So k is log 2 of n, because log 2 of n is just log of n divided by log 2. And what I need to do now is, I have my solution for k, and I need to plug this wherever I had a k. We will test this now. So I'm plugging this in, and we're continuing down here. So we said t of n, the pattern was t of n divided by 2 to the k plus k. So this was just the one from up here. And I'm plugging now concrete values for k in here. So I can say this is t of n, and I'm writing in yellow the values of k, 2 to the k, but k is log 2 of n, plus k, which is log 2 n. Now we can simplify this a little bit. Because what I have here is 2 to the power of log 2n. That's just n. So t of n divided by n plus log 2 of n. And t of n divided by n is 1 plus our log 2 of n. And now I need to know what is t of 1. Do you remember what's t of 1 from before when we looked at the edge case? If you remember it, send it to the chat. And that's 1 because this is this one up here. So, and this is 1 plus log 2n. And now, what is the O complexity of this term? 1 plus log 2n. This is O of what? If you remember it, send it to the chat. So I have 1 plus log 2n, and this is in the order of log n. Because constants disappear, also the base of the log disappears. So what we have here is, this is the O complexity of binary search. Let's revise what we did. We defined the recurrence relation and saw how n develops in the next recursion. We have a corner case as well. And then we try to find a pattern in the recurrence relation. We apply it over and over to itself until we find a pattern for k. K depends on n, and for this n divided by 2 to the k must be for the corner case. We solve for k, and we have concrete values, or concrete one for k. We plug it into the pattern of the recurrence relation and simplify it. We need to look for the corner case and then eventually apply the binary search, apply the O complexity to it. This looks more difficult than it is. And for the remaining 10 minutes today, we will do another one for further practice. I will just share the slides again. So this is what we just did. We have the binary search. Just written this out for you and we solved it. So this is for your revision. We have one more recursive algorithm that we will briefly study. It's not a complete algorithm yet. It's rather a pattern. The function is called do something. It works on a list and has a left and right index. We calculate a middle index, so something we have done before. And as long as left is less than right, we do a recursive call from the left to the middle and do a recursive call from the middle plus 1 to right. So we do a recursive call on the left interval. We do after that a recursive call on the right interval. And then we combine everything in the list from left to right. So this is not a concrete algorithm. It's just a pattern. And this pattern is something we will see again when we look, for example, at sorting. And today we need maybe 10 minutes longer, but then, or 5 to 10 minutes longer, but then we can finish this. So we still need a little bit of time, and then you have enough time for your revision. So we do something for half the interval, we do something for the other half of the interval, and then so recursive calls for the left and right halves of the interval, and then we work on the whole interval. And this is like a pattern of an algorithm. And we will briefly look at this now and see what the recurrence relation of this algorithm could look like. This is called the other, or say for some recursive algorithm, so some recursive algorithm from slides. This one we can also try to describe as a recurrence relation. And there's obviously a corner case. We say for t of 1, it's 1. Just terminates when we have only one element left because we said left needs to be less than right. And the t of n is we are looking at half the interval for a recursive call. Then we are looking at the other half, doing a recursive call. And eventually we are doing the combination. Combination is not a recursive call, but we rather combine something from these two intervals. We can simplify, so it's t of n half, left half, plus t of n half for the other half, plus n. And we can just simplify this and say it's 2 times t of n half plus n. We don't need to add more constants here because the constants would anyway disappear because we have n, because we need to do the combination on all entries. So we need to look at all entries. But t of n half plus t of n half is 2 times t of n half. And then we do the combination. So let's see if we can find a pattern in this recurrence relation. So we said t of n is 2 times t of n half plus n. And we continue with this. So 2 times something plus our n. And I'm applying now the recurrence relation to itself for t of n half. And we saw for t of n half, what we get is this 2 times t of n half plus n. But if n half is put in as n, then this leads to t of n divided by 4. And if I put in for n, n half, it's n half. So I'm writing this is 2 times t of n divided by 4 because I'm putting as the parameter n half in here. And then n half halved is n divided by 4 plus n, but the parameter n was n half. So it's n half. We can try to simplify this, and we see we have a 2 times 2, which is 4 t of n divided by 4. And we multiply this 2 with n half, so this is plus n. And then we still have this old n from before. So what I see is I have a 4 here, a 4 there, and an n plus n. If you try this at home more, you will, or we see it now briefly, but also try it at home for further practice. If I do this again, it will be 8t of n divided by 8 plus n plus the 2 n's from before. So these were the n's. Do you see a pattern, how this is evolving? What if you see a pattern, maybe thumbs up. If you don't see a pattern, that's also fine. Do you want to tell us the pattern? What pattern you see? The pattern I see is, and I'll wait for you a few seconds and see if there's some response. So we have an 8, and we have 3 n's. We got a pattern suggestion now. The pattern suggestion is it's 2 to the k, because this would be 2 to the 3 is 8, t of n divided by 2 to the k plus k many n's, because we have 2 to the 3 is 8, 2 to the 3, and 3n. So this is the k. Now, we won't need to ask when does this finish. N divided by 2 to the k must be 1 to finish. So let's say again, n, n divided by 2 to the k must be 1. So we know from before, just as before, that k is the binary logarithm of n. We've done this with the past example to solve for k, so we just assume this here. And now we need to plug this again for k in here, wherever we have the k. Up here, it was a little bit simpler when we plugged it in because we only had the k here and there, but you need to plug this in for all the k's. So we said it's t of n, and I'm putting the n's soon in, the k's in very soon. 2 to the k, 2 to the k, and kn. And we are plugging this in. It's 2 to the log 2n times t of n divided by 2 to the log 2n plus log 2n. And just to make sure that we multiply this correctly, I've put these parentheses around it. Now we simplify it. 2 to the log 2n. So we start with this one here. This is n, because 2 to the log 2 of n. This one is as before. We said that, well, I'll write it out. T of n divided by n, because the log 2 to the power of log 2n is n, plus, and now I just change the order of this, is our log 2n. So I've just flipped these two, but it's a product, so n times log 2n. This one here, n divided by n is 1, and t of 1 is 1. So this is n times 1 plus n times log 2n. Now, big question. So this whole term is O of what? So I have n plus n times log 2n. Got the right suggestion already in the chat. Eventually, n log n is higher than n. So this is O of n log n. So O of n log n is the complexity of this algorithm pattern we looked at. And this kind of pattern is something you will see again when we look at sorting. Because sorting does a little bit more, and then we're done with sorting. So just need to add a little bit here, and then you have, for example, one of the sorting algorithms we will study. The recurrence relation I've just solved is here. All these steps we've done together. It's with a little bit more text, just for your revision. There are two more recurrence relations that I want you to solve at home. They have a different pattern. T of n is T of n minus 1 plus 3n. And here we have a different edge case. It's not T of 1, it's T of 0 is 1. And here you need to apply T of n to itself until you see a pattern. It looks a bit more complex. There is the solution here in the slides, but try solving it on your own first. And we keep doing the recursion, and then this is T of n is T of n minus 1 plus 3n. Now here you apply the recursion, so this is T of n minus 1, so T of n minus 2. This is the old 3tn, and this is the 3tn where n is minus 1. And you keep doing this and you will find a pattern, which is maybe a bit more tricky. And then you need to find out when this finishes. So n minus k must be 0. So k must be equal to n. And then you'd say k is equals n, and you just plug it in here from before. And you try to find a solution, which is this one here. And there's an O complexity of O of n squared. So it's a bit more tricky, but it's your homework, and the solution is in here. And there's yet another recurrence relation, which looks something like this. Always pay attention to the corner case if it's t of 1, t of 0. And there's yet another recurrence relation, and the slides show you how to solve it and to find the O complexity. I've told you before, when we looked at the towers of Hanoi, their O complexity is O of 2 to the n. And it turns out you can describe the towers of Hanoi as a recurrence relation. Because what it does is, it does some constant work, the towers of Hanoi. We've seen it before. It does a recursive call first on moving all the disks except of one to the auxiliary stack, then moves the moves the largest one to the target, and then moves the other stack of n minus 1 from the auxiliary to the target again. So it's t of n minus 1 plus t of n minus 1, so 2 times t of n minus 1 plus 1. And if you use the approach we have just done to solve all of this, so you need to manually solve this recurrence relation. And for these recurrence relations here, you would probably always assume t of 1 is 1. Yeah, t of 1 is 1 is the edge case for all of them. And what I have written here in the table for you in this column is the solution. So this is the O solution for these recurrence relations for t of 1 equals 1. We have seen the binary search already. We have seen this one, we've seen this one here, which was for this algorithm pattern. Concretely, this is something that merge sort would do with a few more lines of code. And this sequential search we saw, the classic linear search, can also be described as a recurrence relation. You can also try to implement the linear search, sequential search as a recursive algorithm. We will look at tree traversal, we will look at merge sort, we will look at selection sort. Maybe the names of the algorithms that you don't know yet, they don't matter. But what matters are these recurrence relations. And with the tools I have shown you today, you're able to solve all of these recurrence relations. It's not easy, it will take you a little bit, but solve them at home. And then there is still one more task that you can try at home on the weekend. There is a very, or even a um, more sophisticated one. And it's something like, and I've just noticed actually after all the years, there's a typo in it. But so when I fix typos, I will upload this at the end of the term. So what this one says, A of n is 1 for where n is 0, 1, 2, or 3. And for larger n's, where n is 4, this is a of n minus 1 plus a of n minus 2 plus a of n minus 3 plus a of n minus 4. Then solve this one. This one will be more difficult, but always remember that with the O notation, we take an upper boundary. Maybe if this one here is too tough to solve, it's actually more complex than the Fibonacci numbers, what we are trying to solve here. Imagine maybe there's an upper function that you can describe more easily and solve for that one. But this is really the expert task. Start with this one and the two other recurrence relations I had put here. I know solving recurrence relations manually is tricky, but next week we will see the master theorem. And the master theorem is a more structured approach to solving a certain class of recurrence relations. Not all, but for a certain type of recurrence relations, we can solve them much easier rather than always doing this manual work. But we still need this manual work because there will be a lot of recurrence relations for which we don't have a structured approach. We will do this next week, and next week we will also see how to speed up recursion. And next week in the lab, there is some work here for you in the recurrence for recursion. You can work on this already. You can also solve the recurrence relations for these functions either manually, you have all the tools available, or with this master theorem we do next week, you will be able to solve this one here much more easy. But this, you can already work on this, and you don't need a master theorem for it. It will only make it easier, but you can anyway implement them already. Are there any questions, or you're all good? If you're all good, maybe thumbs up. If there are any questions, thumbs down, and I'll wait for you. With all of you being okay, I know it's lots of maths today. Make sure you're familiar with recurrence relations next week so we can actually continue this. And it will take a while to practice this, I know that, but it's a very important skill, and we will need it when we look at other recursive algorithms later in this course. So I wish you a good weekend and take care and goodbye.